In this video, we'll work on two more methods that will take a certain equation and turn them in. One will be a separable equation, and then the back half, the second method, will turn it into a first order linear. So the first thing first, we need to discuss a new definition. If a function has the property where I plug t's in, do a multiple of t with both x and y, and I can get that to t to some power times the original function, then this function is said to be homogeneous. All right, that's just the definition of that. For example, okay, if you take this next one, this is x cubed y plus y cubed. Well, if I plug in tx and ty, plug them both into the cubes, right? Each one has a t cube, so we factor it out. Well, then I have t cubed times, that's the original function. So this would be homogeneous, as where this x cubed plus y cubed plus 1 would not be. If you plug in tx, you'd still get that t cubed, but it would be like a t cubed x cubed plus y cubed, and then that plus 1 would keep it from being t to the third times the original function, because there's no t to the third to it. Okay, so if a first order differential equation is in differential form, remember that some function of x and y times dx, some function of x and y times dy, and we want it to be equal to 0, okay? This diffie in this form is said to be homogeneous if both functions, m and n, and they call them coefficient functions, are homogeneous function to the same degree. Meaning, when I check to see if they're homogeneous, the alpha up here in our definition is the degree. So it would need to be the same for both. Okay, if this happens, and some theory, and I'm just going to leave it there. If you'd like to see it in the book, they drag you through the theory. It's pretty heavy. It's not bad. I'd encourage you to go read it and see if you can follow through it. We're not going to do that. I'm just going to show you by example how it will work out. Okay, when this works out, when you have two homogeneous functions of the same degree, you can make a substitution of y equals ux and x equals vy. There's some indicators on that, and I feel like reps are going to be your best way of understanding which one you should use. Usually, what I do is I'm looking for the one that provides me with the least amount of work. I think we are all pretty the same when it comes to that. I think most people. Um, so u and v are new variables, and we'll treat them as so. So let's do an example. This is how I said I wanted to show you how it works rather than with theory on this one. Okay, first things first, I'm going to label each function. Mxy is y squared plus yx. Okay, and then n of xy is equal to x squared. Okay, let's check to see if they're homogeneous. So I plug in a tx and a ty. Plug those both in. I got ty squared plus ty times tx. All right, if I do that, I get you can see there's t squared in both. And that's times y squared, and then I'd have a yx here left. Well, that's just actually t squared times m of xy. So this one is homogeneous, degree 2. And then we have to do the other one. So we'll do n of tx, ty is equal to tx squared, which is equal to t squared, x squared, and that is t squared times n of xy. All right, so that implies, this double arrow means implies, that the DE is homogeneous. Genius. And that is due to both of them being degree 2. All right, so now we can solve. I'm going to pick, I think in this one, it really wouldn't matter which one you choose, but I'm going to choose y equals ux. I forgot my u. And now if I'm going to do a replacement, though, it's not just y in my equation there. I also have a dy that I got to take care of. So I'm going to take the derivative, but use it like in differential form like we do for u subs. So dy then is equal to, now u is a variable now, so this requires the product rule. Right, so I'll take the variable u, that derivative is 1, so I get an x du plus, and then the product rule says now take the variable x derivative, so I just get a u dx. So I'm going to have to make that replacement also into my equation. All right, so I'm going to rewrite the equation so I can see exactly what I'm plugging into without having to scroll up and down. It's x squared dy equals 0. So I'm going to replace all y's and dy. So we get, subtract red, right? We're going to get Let me put it in brackets to make it a little bit easier to deal with. I'm going to get ux squared plus ux times x dx. That's fine to stay in there. And then x squared, and it's going to be times all of what we just wrote up there. X du plus u dx. That's the product rule given from our substitution, and this still equals 0. All right. Notice everything here is with the dx. I'm going to leave that alone for a minute, and then I'm going to kind of color code. This will go here with du, but it will also go here with the dx. So if I put it together, all the dx's, I'm just going to do it in one. And let's go ahead and multiply things together. U squared, x squared. All right. And then plus u x squared dx. Oh, and then let's go ahead and add the other dx, which is going to be u x squared. That's from over here. Dx. Plus, and then now just the stuff with du is going to be x cubed, right, du equals 0 still. Don't forget that. That's important. All right. And then notice, okay, we got to figure out how we're going to figure this out. So we get, if you notice, we all have U's there. I feel like there is a mistake somewhere, but I don't think so. Oh, okay. So there's a U. Just got a feeling. Notice there's a U in everything. Actually, let's add like terms first. So I got U squared x squared plus 2u x squared dx plus, and then the x cubed du equals 0. All right. And we can notice that there's an x squared in both over there. All right. So I'm going to go ahead and factor out, and I'm going to go ahead and move some things around. So there's an x squared over here with this dx. So I'm going to factor out, and that leaves me with u squared plus 2u dx. And then I'm going to go ahead and minus, so I get x cubed du. I'm going to drop the brackets. All right, now I know I can see where to go. Okay, I'm going to get negative 1 over x dx equals, and then we're going to get 1 over u, and I'm going to go ahead and put u plus 2. I'm going to go ahead and factor it. I got to make this smaller because we need some more room. Apologize if you're writing the same size as me. Try and write it big enough so it's not so small in the video. All right, so now I would do that same thing, but I'm going to integrate both sides. All right, and I get negative ln of x equals, and we'll go ahead and put the plus c over here with the x. And then this is going to require some partial fraction decomposition. So we're going to get 1 over u times u plus 2 equals a over u plus b over u plus 2. Right, that's 1 equals a times u plus 2 plus b times u. Okay, u equals 0 would result in a equaling 1/2. U equaling negative 2 is going to result in b being a negative 1/2. All right, so that is now the integral of 1/2 over u plus negative 1/2 over u plus 2 du. Right, and bring it down again. Actually, I'm just going to add a new page. Let's do that. Okay, so I have that now. I wish this would go away. Sorry, it's being weird. There we go. All right, so I get negative ln of x plus c equals, and then I'm going to get a 1/2 ln of u minus 1/2 ln of u plus 2. Just an easy u sub there if you really want to think through it. So then what we have next is we just got to replace u. Well, if y was u equals x, then u is equal to y over x. So I just have to replace it. I get negative ln of x plus c equals 1/2 ln of, okay, and then I just replace it. I got y over x minus 1/2 ln of y over x plus 2. And Solving for y there would be, I think, pretty difficult. So I think I'm going to go with the implicit solution here. So that would be our solution. So the whole idea, and this will be a common theme, um, that we will take harder Diffie Qs, more difficult ones, do something with them, change them into a Diffie Q that we know how to solve. Like in this case, we changed it to a separable Diffie Q. Okay, hope this makes sense.